Hello, my name is Hongji Kim and I'm from Computational Cognitive Affective Neuroscience Lab in Choong-Wan University and Center for Neuroscience Imaging Research. Today, I'll present my work, recently published in PNAS, about brain decoding of spontaneous thought. Our mind never rests. When we are taking rest or even sleeping, our mind spontaneously wanders from the past to the future and across many concepts. However, assessing our spontaneous thought is difficult because it occurs freely with minimal conscious constraints, and paying attention to spontaneous thought can change the nature of spontaneous thought itself. For these reasons, measuring some aspects of spontaneous thought directly from brain activity, such as fMRI signals, would be useful for the understanding of cognitive processes underlying spontaneous thoughts and the clinical application. To effectively induce brain representations that resemble those of spontaneous thought, we chose to use narratives as stimuli. In this study, among multiple dimensions of spontaneous thought, we particularly focused on self-relevance and valence. Dimensionality reduction analysis conducted in previous studies showed that these two measures were among the most central dimensions that can serve as summaries of other content dimensions. The three major goals of the current study include, first, developing fMRI multivariate pattern-based predictive models of self-relevance and valence. To develop the predictive models, we used fMRI data while reading stories as the feature and story survey ratings of self-relevance and valence as the outcome. The second goal was to compare and interpret the models of self-relevance and valence using region and network level analysis and virtual isolation and lesion analysis. The last goal was testing the predictive models on the resting state fMRI data with and without intermittent thought sampling probes. To achieve the research goals that I just explained, we conducted a 2-day experiment. On day 1, we conducted a one-on-one interview with participants to create personal stories to use as stimuli in the fMRI experiment. On day 2, participants underwent the story reading and thought sampling tasks in the scanner. In the thought sampling task, we asked participants to think freely and verbally report what was in their mind with a few words intermittently. During the story reading task, participants read 4 personal stories which were created for each participant and 6 common stories which were the same across participants. After the scan, we conducted a post-scan survey on words and stories. For the story survey, participants read the stories again and rated their perceived levels of self-relevance and valence using continuous ratings. Based on each participant's self-relevance and valence ratings, to effectively disentangle fMRI patterns for those two, we concatenated and quantized the data based on quintiles of 2 dimensions, constructing 25 averaged images per participant. We trained fMRI multivariate pattern-based predictive models using principal component regression with leave one subject out cross-validation and random split cross-validation. This shows the predictive models of self-relevance and valence. The two models showed a weak correlation between the unthresholded whole brain patterns of the predictive weights, while the medial prefrontal cortex, which is known to be important for both self-relevance and valence, showed a weak but larger correlation than the whole brain. This suggests the existence of overlapping representations between self-relevance and valence within the MPFC. These violin plots show the performance of each model, where each dot meaning each participant. And this shows for self-relevance, as you can imagine, the self-relevance ratings were generally higher in personal stories when compared to the common stories. Each line indicates each participant here, and this was well tracked by the self-relevance model response as well. Also, we could successfully classify personal and common stories based on the model response. This last plot shows the word representations of valence model in TR by TR word analysis. We used the adjusted selection frequency based on valence to examine the relative importance of words based on both valence ratings or valence model responses. To make the long story short, it shows that our valence model could well capture the actual valence ratings in these stories. We examined which features were important for predicting self-relevance and valence using the virtual isolation analysis, which calculated prediction performance based on a single large-scale network, region, or searchlight at a time. First, this plot shows the virtual isolation analysis result for predicting self-relevance and valence in large-scale networks and some ROIs. Each colored dot represents the prediction outcome correlations for each network or region with bootstrap tests. You can see that the default mode, ventral attention, and frontoparietal networks were important for both self-relevance and valence prediction. The next plot shows the searchlight-based virtual isolation analysis results for the self-relevance and the valence model. Anterior insula and anterior mid-cingulate cortex were among the important features for decoding self-relevance. And for valence, left TPJ, TP, and DMPFC were the important features. Next, we tested the models on the fMRI data from the thought sampling task, in which we asked participants to report what they were thinking every 50 seconds with jitters. Given that the verbal responses to thought sampling are most likely to be based on the thought contents just before the reporting onset, and considering the hemodynamic delay, as shown in the figure, our time of interest was a 10 TR, which is total of about 5 seconds time window around the reporting onset. Both predictions of self-relevance and valence showed the best prediction performances at the time of interest period, and this was consistent when we used the time bins of 10 TRs. Lastly, we tested the self-relevance and valence models on the resting state fMRI data from two independent datasets. Here, I'm showing only one dataset with 90 participants, but in the supplementary information, we also have another dataset with 60 people. At the end of the resting scan, participants reported the levels of self-relevance and valence for the thoughts they had during the resting scan. Given that the answers to the post-resting survey were likely to be based on participants' thoughts around the end of the scan, we tested the model performances using average data from the end of the scan. As shown in the figure, the self-relevance and valence models both showed significant predictions for the self-relevance and valence ratings around the same time window, when the data of the last 31 TRs, which is about 14 seconds, were averaged, and the prediction performance were around 0.2 and 0.3 for predicting self-relevance and valence. To summarize, we developed brain-based predictive models of self-relevance and valence by using story reading data, and these models could also decode the affective states of free thinking and resting states. Overall, we believe that our study provides an important step toward understanding the internal states and emotions during daydreaming. Thank you for listening. 근데 thank you for listening 여기다 하는 거 맞나요? 마지막에 thank you 슬라이드 있긴 한데. Self-relevance and valence using
그거지?
너무 어려운 문제인데? 저 누가 썼지? 됐어.